Hi everyone, good evening. Welcome to my YouTube channel. Today I'm going to be talking about photoelectricity. So the PDF you can see now is what I'm working on, and I'm going to be sharing it with you guys so that you can understand it better. If you want to get a full PDF, check the description below. So today we're talking about photoelectricity. What is photoelectricity, or what is photoelectric effect? The photoelectric effect is the emission of electrons when electromagnetic radiation such as light hits a metal. So what happens is that when an incident electromagnetic ray of light hits a metal, electrons are emitted from the surface of the metal. But it doesn't just entail an electromagnetic wave hitting the metal and electrons leaving. There are some other things that have to happen, some parameters that have to be met before these electrons can be emitted. Now, if you look at the diagram below, you can see that this diagram basically explains everything that photoelectricity means. We see this incident electromagnetic radiation hitting the surface of the metal and then making contact with the electrons in the metal. And on the other end, we see electrons leaving the metal. So these electrons have been dislodged because photoelectricity has happened, it has taken place. So now I'm going to be explaining the parameters that have to be met before electrons can be emitted. So the first parameter that has to be met, now we're going to be talking about, is threshold frequency. Threshold frequency is that frequency of light that will vibrate or cause an electron to dislodge from a metallic surface. So what happens is that when electromagnetic radiation such as light hits a metal, sometimes it's not all the time that the electrons are emitted. This is due to the threshold frequency of the metal. If the frequency of the electromagnetic radiation isn't equal to or greater than the threshold frequency of the metal, electrons won't be emitted. Now let me take it again. If the frequency of the electromagnetic radiation is not equal to or greater than the threshold frequency of the metal, electrons will be emitted. For electrons to be emitted, the threshold frequency must be equal to, no, for electrons to be emitted, the frequency of the electromagnetic radiation must be equal to or greater than the threshold frequency of the metal. So threshold frequency is denoted by FO. Threshold frequency is denoted by FO. As we can see here, this is what is denoted by. Now the next one we're going to be talking about is work function, or threshold work function. What is threshold work function? This is like the second phase. After threshold frequency, this is the second phase. Threshold work function is the minimum amount of energy required to remove or eject an electron from the surface of the metal. So during the threshold frequency stage, when this light hits the surface of the metal, and then the frequency of the light is greater than the threshold frequency of the metal, what happens is that the frequency of the light only dislodges the metal. It only dislodges the electron from the surface of the metal. It doesn't make the electron escape totally or leave the surface of the metal. What work function does is that it gives the electron enough energy to escape from the surface of the metal. By escape, if you go back to the diagram above, this is what I mean. Now these two electrons that have escaped the surface of the metal were dislodged by threshold frequency because the frequency of the electromagnetic radiation was greater than or equal to the threshold frequency of the metal. So they were dislodged, they were released, but they are not yet escaped from the surface of the metal. So work function gave them enough energy to be dislodged, to be removed, to escape from the surface of the metal. And then work function has its formula. We can actually find work function. The formula for work function is given here. Work function is equals to HF, which means work function is equals to Planck's constant times threshold frequency. Now you can see how work function and threshold frequency work hand in hand mathematically. To find work function, you multiply threshold frequency times Planck's constant. Planck's constant is 6.6 times 10 to the minus 34 joules. So in any question you are solving, that involves Planck's constant, you are always going to give you the value because it's a constant. 6.6 times 10 to the minus 34 joules. Now, after talking about threshold frequency, we now need to understand the basics of these equations, because these questions can come in different ways, different forms. Now we're going to be going to my word. I'm going to explain. From the beginning, we need to know that speed of light is equals to frequency times wavelength. Speed of light is equal to frequency times wavelength. We also need to understand that frequency is equal to speed of light divided by wavelength. And we also need to understand that wavelength is equal to speed of light divided by frequency. So once you understand this formula, once you just basically know speed of light is equal to frequency times wavelength, you know how to manipulate this formula into making it fit into the question you're trying to solve. So from that, we can now proceed into the calculation. In questions in photoelectricity, they are going to ask you to calculate the energy of a photon. So what is energy of a photon? Energy of a photon, E, is equals to hf. Energy of a photon is equals to Planck's constant times frequency. Energy of a photon is equals to Planck's constant times frequency. You see these formulas, once you understand the first one, you know how to manipulate the second, third one to make it fit to the question. Since we know that energy of a photon is equals to Planck's constant times frequency, and we know from above that frequency is equals to speed of light over wavelength, in a case where we weren't given frequency but we were given speed of light and wavelength and Planck's constant, what are you going to do? All we're going to do is insert F is equals to frequency is equals to speed of light over wavelength into this equation. So if you are given a question where you were only given Planck's constant, speed of light and wavelength, and they asked you to solve for energy of a photon, what you do is you say energy is equals to Planck's constant times speed of light over wavelength. You see, we're getting somewhere. Planck's energy of a photon is equals to Planck's constant times speed of light over wavelength. Now let's check some simple calculations that use this formula. Now if you scroll down in my PDF to check for some questions, don't forget, if you want to see or contact me for the PDF, just check my bio and then you should be able to reach me. We're almost there. Yeah. So don't forget those formulas. Energy of a photon is equals to Planck's constant times frequency. But if you were always given frequency, you can always do Planck's constant. Energy of a photon is equals to Planck's constant times speed of light over wavelength. So we're going to be taking this question. If the speed of light is 3 times 10 raised to power 8 meters per second, calculate the frequency of light if the wavelength is 7.80 times 10 to the power minus 7. So the first thing you should always do when you are solving a question, a physics question, is to write out all the parameters you have been given. Okay, we know we'll be given speed of light, we'll be given wavelength, but they are asking us to find frequency. So from the formula, see speed of light is equal to frequency times wavelength. We know that, oh, okay, we can just make frequency the subject of the formula. Now, if we come back to the question, they gave us speed of light, they gave us wavelength, they are asking for frequency. So basically, it is this formula we're using. They gave us speed of light, they gave us wavelength, and now they're asking for frequency. When they give you questions, you need to check all the parameters I'm given and cross-check with all the formulas you know to pick the right formula that suits the question. So when you've picked the right formula that suits the question, you now go ahead and calculate it. From this question now, we use the equation speed of light is equal to frequency times wavelength. So when we make frequency the subject of the formula, it becomes frequency is equal to speed of light over wavelength. So after that, we now put in our value, speed of frequency is equal to speed of light over wavelength. Then when we calculate it, it's going to be this is the answer, 0.3846 times 10 to the power 14 hertz. Now don't forget, when you're solving, you should always put your units after solving. The unit of frequency is hertz. So after that, we're now going to check for another question that can that can explain our equations better. Now the next question explains this third formula. Sorry, I mean the next question. In the next question, we're going to use this third formula. So if we check the question and read it, the question says calculate the energy carried by an X-ray of wavelength 6.0 times 10 to the power minus 10 meter, and then they gave the Planck's constant, they gave speed of light. So they're asking us to find the energy, but we know okay, they didn't give us frequency, they only gave wavelength and Planck's constant and speed of light. So we write out our parameters first. They gave us speed of light, we're giving wavelength, and then we're giving Planck's constant, and then instead we should find the energy. We know the energy of a photon is equals to E is equals to HF, which is energy is equals to Planck's constant times frequency. But in the question we see that frequency was not given. So in this case, what do? Remember that frequency is equal to speed of light over wavelength. So what do? We put frequency is equal to speed of light over wavelength, and we put frequency equal to speed of light over wavelength into this equation. So it becomes energy is equal to Planck's constant times speed of light over wavelength. So when you come back to the question now, we see what I solved. It says but frequency was not given, but we know that the formula for frequency is equals to speed of light over wavelength. So we now substitute formula for frequency into E is equals to HF. So when we do that, we have E is equals to HC over wavelength. You have to remember this equation. You need to know the basics from speed of light is equals to frequency times wavelength, and then once you know that, you know how to maneuver your way into getting this equation. So after getting this equation, we substitute our values, and then we get our answer, 3.3 times 10 to the power minus 16 joules. So if we now go to the next question and check, we can see this question is similar to the last one. You can just decide to pause the video and attempt these questions. So the next question says, what is the energy of an incident light of wavelength 10 raised to the power minus 7 meter? Okay, what is the energy with which an incident light of wavelength 10 raised to the power minus 7 meter falls on a metal and electrons are emitted? So you're asking for the energy that the incident light has, incident radiation, electromagnetic radiation has. What energy does it have? They gave us speed of light, writing out our parameters. They gave us speed of light, they gave us wavelength, Planck's constant. But remember, and check, they didn't give us frequency, and they said we should find the energy. So from the last question, we already understand that, okay, since we're not giving frequency and we're giving wavelength, and speed of light is present and Planck's constant, we can just use the formula energy of a photon is equal to Planck's constant times frequency times speed of light over wavelength. Yeah, so once we do that, we input our values into it, and then we write our answer and units. Don't forget, we must always write our units. The unit of frequency is hertz, the unit of energy is joules. So after that, let's now check the next question. This one is a bit tricky, but it is actually easy to understand. Before we attempt this question, let us go back to my Microsoft Word to explain. So we know the energy of a photon is equal to HF. But what if we're given an energy diagram, an energy level diagram, and then we're asked to calculate the energy? Let's now look at this question. It says an atom assumed to have zero energy in ground state and its energy in the first, second, and third state are. They now give what the energies in the first, second, and third states are respectively. They now said what is the wavelength of the photon which will excite the atom from the first excited state to the second excited state. So here, look at the question. They said what is the wavelength? We said that we're given 3 levels of energies, actually 4, from the ground state to the third one, making 4 levels of energies. And then we've not seen a question like this before. What do? Let's go back to our Microsoft Word. So we know E is equals to HF. But what if we're given two energies? What we do is we do E2 minus E1 is equal to HF. Now what have we done here? We're looking for the amount of energy, like We're looking for the amount of energy, the proper amount of energy. So we subtract the higher one minus the lower one and then equates it to HF. We equate it to HF. Now, if we check the question, it says that we should find the wavelength. What is the wavelength of the photon that would excite the atom from the first excited state to the second excited state? So one thing about this question is that we've not talked about is excited state. So electrons can get excited in various states. An electron that has not been come in contact with any electron is in ground state. When it gets excited, or when it receives energy from a photon or an electromagnetic wave, it gets excited and keeps moving to excited states until it eventually escapes from the surface of the metal. So now they're asking us what is the wavelength of the photon that would excite it, that will make it move from the first excited state to the second excited state. So when we now come down, we write out our formulas. The speed of light, we write it down. Planck's constant, we write it down. First excited state, we write it down. Second excited state, we write it down. The third excited state, we write it down. But they're asking for the wavelength. Check the question again. They're asking for what is the wavelength of the photon that would excite the atom from the first excited state to the second excited state. So when you do that, when you see a question like this, what you first want to do is you need to draw an energy level diagram. From here, we see and the electron is in ground state. E0 is equal to ground state. So the first excited state, this is the value. The second excited state, this is value. The third excited state, this is value. So when we've drawn our energy level diagram, we now come back to the question. The question says, what is the wavelength of the photon that will excite the atom from first excited state to the second? So they're asking you what wavelength must the photon have? What wavelength must it have to get excited? Must the electron have to get excited to the second excited state? So what we do is that the next step we take, is now finding the right formula for the question. We now go back, look at all the parameters we have, and then we come down and say, okay, they said we should find the wavelength, but they didn't give us frequency. And then when you are not given frequency in a question, you know the formula for frequency, but you are not given frequency. You just use the formula and put the formula for frequency into the main equation. E is equals to HF. That means E is equals to HC over wavelength. So here, taking this into, we know that energy changes as the atom makes a transition from the first excited state to the second excited state. We need to analyze it all. So we're now like E is equals to HC over wavelength because frequency was not given, and energy E is equal to E2 minus E1. Like I said before, a change in energy level. Whenever there's a change in energy level, you want to subtract the higher energy level from, you want to subtract the lower energy level from the higher energy level. That's right. Here you have energy E is equal to E2 minus E1. So we know that since E is equals to HC over wavelength, we can also say that and E is equals to E2 minus E1. We can now equate it together. It's not be E2 is equal to it's not be E2 minus E1 is equal to HC over wavelength. So after that, then we now check the question again. Okay, we're told to find wavelength. So you now change subject of the formula from your mathematics. Change your subject of formula. It now becomes wavelength is equals to Planck's constant and speed of light over the second excited state minus the first excited state. So when you substitute your values into it, you now get this. Now in my next video, we're going to be talking about Einstein's equation. Now the Einstein's equation might be a little tricky because there are a lot of things that are going to it. There are a lot of questions that can come in different forms, but it's just basically understanding the basics. From the first formula, C is equals to speed of light is equals to frequency and wavelength. Once you understand these formulas and take them slowly and break them down, trust me, Einstein's equation is going to be very easy. Thank you for watching this video. To view my video on photoelectricity, click the card that shows up, and please don't forget to like, share and subscribe for more. Thank you.